Go to the cloud.
This meeting is being recorded.
Oh, there you go. Thank you very much, everyone. Welcome to HRAI's webinar, Low GWP Refrigerants, Importance of Refrigerant Specification and Safe Handling. Today, this is being led by Bill Yeo, Market Segment Manager of Refrigerants for Messer Canada Inc. Bill knows what he's talking about. He's got over 25 years experience in the industrial chemical market, as well as providing sustainable and secure product destruction solutions for pharmaceutical, consumer packaged, and industrial product and process materials. That must be a big business card to fit all that in. Hey, Bill.
Yeah, definitely.
So we're very happy to have Bill here. He's got a great presentation all lined up for you, and I'm going to exit. Just before that, though, just a reminder, this is a recorded presentation. You can find it on HRAI's website after the fact, and we are taking questions, so pop those in the chat. The button's just down at the bottom of your screen, or you can pop them in the Q&A as well. And if you don't get to them at the time, we will save them for the near the end of the presentation. And with that, I am going to turn off my camera and hand things over to Bill.
Great. Thanks very much for the introduction. Good afternoon, everybody. I'm going to talk about natural refrigerants today and kind of a different approach, more of the characteristics of them, specification, the quality, and what's important for refrigeration mechanics and companies to realize when they're purchasing natural refrigerants. So natural refrigerants occur in nature, but they are actually manufactured industrially to come up with the chemistry behind them. So ammonia, although it occurs naturally, it has to be processed to be able to meet the specification of ammonia. Same with CO2 and hydrocarbons. They all exist in nature, but they have to be manufactured to within specifications to be able to use in refrigeration systems. Some of the benefits of the natural refrigerants overall: high performance. For the most part, they're very efficient. The coefficient of performance for them is very good compared to other refrigerants in the marketplace. They are very cost competitive. I'll talk about that in a little more detail later on in the presentation. Compatibility in terms of metallurgy and system components, ammonia, CO2, and hydrocarbons have a very good compatibility with either metallurgy of systems when they're designed correctly, and just compatibility in terms of health, safety, and the environment. Low impact. They have a very low global warming potential, if not 1, sometimes 0. And the ODS, ozone depleting, is very low as well. From a regulatory standpoint, they aren't regulated by the Montreal or Kigali Protocol. There's no legislation in place to phase down or phase out these refrigerants. They've been around for many, many years and will be still around for many years because of their chemical makeup and compatibility. So natural refrigerants, the main issues surrounding them in terms of purity are moisture and uncondensable gases such as oxygen and nitrogen. In certain cases, like carbon dioxide, R744, oil, and hydrocarbons can be an issue. The same within ammonia systems. So it's very important to know when you're purchasing these refrigerants what the levels of contamination is, what the specification is of the product that you're actually buying. And in terms of specification, the American Heating Refrigeration Institute, which is the AHRI, as well as the International Institute of Ammonia Refrigeration, which is IIAR. Most of you have probably heard of those organizations before. They publish a specification for different refrigerants. And of course, these natural refrigerants have a specification, and it's very important to know what that is in terms of when you're buying these refrigerants. The other thing to reference is what is the equipment manufacturer specification that they required for their equipment. Because if you buy the wrong refrigerant and purity, there could be some warranty issues affecting the equipment that it's installed in. As well, it could cause damage, which means replacement of some of that equipment. So when purchasing these refrigerants, you should always ask for a product data sheet or a C of A, which is a certificate authenticity, which outlines what is actually in the refrigerant. One of the easiest ways of knowing that you're getting what you're getting is if it's sold as an R744 or R717 or R290 in the product name, that means the supplier knows that this is the correct specification for a refrigerant application. So you shouldn't be just buying ammonia, carbon dioxide, or say propane. You should be buying a product that has the actual refrigerant nomenclature attached to it. The market is definitely changing with regard to refrigerants overall, but also with impacts of natural refrigerants. We're starting to see CO2 R744 show up in the automotive market. So Volkswagen, Mercedes, BMW, they've launched cars that now contain CO2 as a refrigerant, as opposed to say 1234YF or 134A. You'll also see some new refrigerants that are launched, probably won't be on the market in North America until after 2024. That would be the R456A, which actually is a blend of hydrocarbon refrigerant in it. Mobile reefer applications, you're starting to see 404A being replaced with 452A, which is an HFO. But in Europe, there are reefer units that are running R744 CO2 over there. Grocery cabinets, over the last probably 7 to 8 years, we've seen some transition away from the 404A to HFO refrigerants. We are also seeing R744 and a lot of hydrocarbon refrigerants showing up in these grocery and food display cabinets. Cold storage units. Cold storage units have been around for a long time, and historically ammonia has been used there. In certain applications, we're starting to see R744 CO2 show up in those cold storage facilities, especially in a food processing plant where they can use a lot of waste heat as well as requiring cold storage. Ammonia, typically we've seen that historically always used in ice rinks, community centers, that type of thing. What we're starting to see over the last, say, 5 years is R744 showing up as a refrigerant being used. And the idea behind that is there's a lot of heat reclamation equipment in a hockey rink, the water to flood the ice, the heat required to heat the dressing rooms and the stands, that type of thing. So all the waste heat from the CO2 refrigeration system can be used in other applications within the recreation or ice rink facility. Safety standards, it's important to note that whenever you're dealing with a natural refrigerant, you have to know the safety standard, how to handle it properly, how to use it and apply it properly. And the ASHRAE standard 34 basically outlines that. You can look up each of the refrigerants under the standard and it'll tell you how to use them. Hydrocarbon refrigerants are typically in the A3 classification, safety group, lower toxicity but very high flammability. Ammonia has a high toxicity, but it's a relatively non-flammable refrigerant. It's classified as a B2L refrigerant. And then carbon dioxide, very low flammability and a slight toxicity. So it would be an A1 refrigerant. So we're really right across the chart in terms of the ASHRAE standard 34. And again, emphasize the importance of knowing the characteristics of each of the refrigerants and how to handle them properly. So that being said, we'll start talking a little bit specifically about the different natural refrigerants themselves, starting off with R744, carbon dioxide, CO2. Basically, this molecule has been around for a long time and was actually one of the first gases to be used as a refrigerant back in the late 19th century. Following that, in around the 1930s, HCFCs started to show up, and because of their ability to replace CO2 in terms of smaller requirements in building the systems financially, as well as the complexity of the systems, hydrofluorocarbons were used extensively up until people started finding out that they weren't quite that friendly to the environment. They posed a high ozone depletion level as well as high global warming potentials. So in the more recent years, technology has enabled R744 to become more popular in terms of a refrigerant. This is because advances in engineering design controls on R744 CO2 systems have come a long, long way, and the technology around being able to operate these refrigerant systems at a higher ambient outdoor temperature has enabled these systems to compete a lot more effectively. And you know, the other major driving force is the low environmental impact of CO2. It has a global warming potential of 1 because it's the baseline that all the other refrigerants are compared to in the marketplace. So again, 0 ozone depletion, global warming potential of 1, excellent thermodynamic properties, and low energy requirements. A lot of this is due to the ability of the design engineer to engineer a system where the reclaimed heat is reused. It decreases energy requirements in an entire facility. And a lot of times CO2 can be used as a secondary refrigerant along with ammonia or other refrigerants, which expands the ability to use it in various applications in the refrigeration industry. It's non-flammable and mildly toxic. Some of the common applications we see are static and mobile air conditioning, chilled warehousing systems, cold storage, commercial refrigeration, little food cabinets, vending machines. I think it was Coca-Cola was launching the majority of their new vending machines using CO2 as a refrigerant. It's used in a lot of different process applications and really good for low temperature applications. And again, I mentioned it's being used in automotive applications. One of the other advantages in the automotive application is it's actually used in the electric vehicles as well as a heat pump. So it can provide both heating and cooling within the automotive vehicle, which helps reduce the power consumption in the automobile, especially in the heating mode. So the product specification, typically it's supplied in cylinders of various sizes, could range from like 50 kilogram cylinders to 10 kilogram cylinders. For larger demands, it can be delivered in bulk liquid. Depending on the system, you may need a pump to pump the liquid into the refrigerant system. And if the pressure is low enough, you could use the the tanker pressure to push the liquid over into a system. Very important when you're first filling a CO2 system that you pressurize the system with CO2 vapor prior to adding any liquid. And the reason behind that is so that you don't form any dry ice in the system. That can be very detrimental to a CO2 system. The cylinders themselves are quite different than a standard refrigerant HFC or HFO cylinder. These are solid drawn steel cylinders. There's no welds on the cylinders, and that makes them much stronger because the pressure of the cylinders is that much higher. And the cylinder is typically a CGA 320 connection. Another unique feature of these cylinders, you can order them as a vapor cylinder, where the valve, when you open it, would take vapor out of the top. And you could order as a liquid cylinder, where there's actually a dip tube that goes down into the liquid in the cylinder, so that when you open the valve, you get liquid. Some field technicians tend to buy the dip tube, and if they need vapor, they may turn the cylinder on its side or upside down, which it can work, but could present some health and safety issues if not handled correctly. So let's get into specification here and various grades of CO2. And it's kind of a busy slide, but I wanted to give you an idea of why it is so important to order the grade of CO2 that you need for your specific refrigerant application. And again, I'll reference back to the AHRI standard 700. It provides a very good detail of the specification for our 744. The other real important thing is to reference the equipment manual for the equipment, refrigeration equipment, whether it's the compressor or other components of the refrigerant system. So you can buy basic grade CO2, which is a purity of 2, which means 99.0% pure. And then, you work your way down the list. The food grade is 2.5, which is 99.5%. Refrigerant grade, as per the AHRI, is grade 3.0, which is 99.9%. There's other refrigerant grades which are 99.99%. And then you have other grades that are still grade 4, aerobic and Coleman, but typically what differentiates these from the refrigerant grade is the amount of moisture. And I'll talk about the moisture in a little bit more detail. In terms of the grade, the graph demonstrates the grade of CO2, and I did a relative cost. So, the AHRI standard is grade 3, and at times people are actually buying 2.8 because it's a little cheaper, and they think that, we can save some money. But in actual fact, the 2.8 does not have a moisture content that lines up with the standard 700. Typically, that 2.8 could be 20 ppm or above. When you buy grade 3 refrigerant grade with the product name R744, that moisture content would be less than 10 ppm in the liquid phase. And the same with a grade 4 refrigerant. You're getting a little bit higher purity, but the moisture content is exactly the same, less than 10 ppm in the liquid phase. So going from these different lower grades to grade 3, there really isn't a huge cost differentiator. But as you move to a higher purity, it's the dotted line is exponential, so you'll see it's actually higher than an exponential increase in cost. Suggests that we reference the standard 700, grade 3 less than 10 ppm water in the liquid phase is probably the most economical, as well as the recommended grade for refrigerant. A lot of the manufacturers would recommend this grade and moisture content as well. Let's go on to ammonia. We'll talk about this molecule. 1 nitrogen, 3 hydrogens. This is, again, a very environmentally friendly molecule, 0 ozone depleting potential and 0 global warming potential. It has excellent thermodynamic properties, and in the industry is notably the most efficient refrigerant. It has a wide temperature range, which means it can operate in various applications. It is mildly toxic and flammable with a pungent odor, and low cost relative to other refrigerants. But in the last, I guess, 3 to 6 months, the pricing on this chemical has increased substantially. That's because of the price of natural gas going way up and other hydrocarbons associated with natural gas, the price increasing as well. Common applications, there's a ton of food plants out there that use ammonia refrigeration. It's got over 100 years of applications, experience, that type of thing. It's a very popular refrigerant. Cold storage facility, meat processing, commercial refrigeration, industrial heat extraction, ice rinks. It's very popular refrigerant. And because of its great environmental impact in terms of global warming and ozone depleting, it should be around for years. There's a lot of new applications in terms of low charge ammonia systems, which use smaller amounts of ammonia. They're either maintained within a mechanical room or on a rooftop unit, and then they'll use a secondary either refrigerant or water, glycol, or calcium chloride brine to distribute that liquid to pick up other heat from the cooling application. One of the biggest barriers for the use of ammonia is the human health factor. So any ammonia refrigeration system should have ammonia detection and alarms, and it should be very well engineered in terms of if there's an upset with the system, if there's a leak, alarming should activate, ventilation of the room should happen. And typically these mechanical rooms are definitely isolated from other parts of the building. In terms of what's the right grade for ammonia refrigeration, there's various grades that are out there. The one that is the standard is refrigerant grade 3.5 and less than 33 ppm water. The problem with that in Canada is you can't really get a grade 3.5 with less than 33 ppm water. The only one available is actually a grade 4 at less than 35 ppm water. So that refrigerant or a grade of ammonia would be the best suited for Canada, because the other grades aren't really available in Canada. And if you did go to a research grade 5, less than 10 ppm water, the price of that is probably 10 times higher than the metallurgical grade at 4.0. So part of the issues with buying the refrigerant and not having the right grade would be, the interaction of the contaminant level with various components of the refrigeration system, not only chemically, but how they act thermodynamically. So if we have water and oxygen mixing into a ammonia system, say you're feeding a lower grade ammonia to the system, you're going to have issues associated with corrosion within the system. You're going to have these non-condensable gases such as oxygen and CO2, nitrogen collecting on the high side of the system, and they will definitely interfere with the efficiency of the system. Oxygen and a few ppm of ammonia will create stress corrosion cracking on carbon and low alloy steels, and this will significantly impact the life of the system, components and piping. CO2, if it's a contaminant in the ammonia, it'll contribute to forming ammonium carbonate. Again, this is very corrosive and will create corrosion within the system, affecting the life of the components of the system. Nitrogen, again, if there's some oil in the system, it'll cause nitriding, which is also a type of corrosion that will occur in the system. In terms of hydrogen contamination within a refrigerant, really there's not a lot of impact in the ammonia system. So hydrocarbons aren't a real threat. Sulfur dioxide and hydrogen sulfide, these are components that could be impurities in ammonia, and again, these will form acids which will contribute to corrosion in the system. So that's why it's very important when you're purchasing the ammonia that you make sure that the uncondensable gases are as low as possible, and the moisture content is less than 33, 35 ppm in the liquid phase. Let's look at the cylinders themselves, and again, some of the references in terms of what the specification should be. So ASHRAE, American Society of Heating, Refrigeration, Air Conditioning Engineers, they have a standard that basically it's published, and it tells you what the specification of ammonia should be. AHRI, American Heating Refrigeration Institute, and IIAR, they also have standards, and they all line up pretty good. It's 3.8 grade and less than 33 ppm water. So again, I wanted to mention that in Canada, the closest we can get to that in terms of refrigerant grade would be the grade 4, which is 99.99% pure, less than 5 ppm water in the liquid phase, and less than 1 ppm oil. The cylinders, again, for ammonia are very unique, and just so that the audience knows, it's very unusual for companies to invest in ammonia cylinders because they've been around for so long, and the cylinders themselves are very, very expensive. So if there are any cylinders out there, I suggest that you try and return them back to the various suppliers so that they don't have to buy new cylinders. That being said, Messer has invested in the last 2 years in new ammonia cylinders, and some of the features of the cylinders I'll discuss now. The cylinder, if it's got a gooseneck connection on the bottom of the valve, and what this gooseneck connection allows you to do is remove vapor if the gooseneck is turned this way, and the valve outlet would be at the bottom. And by laying the cylinder down like this, you'll get about 60% more vapor coming out of the cylinder than if you have the cylinder in the vertical position, just drawing vapor off the top of the cylinder. The reason for this is the surface area. This would be similar for a lot of other gases in terms of being able to generate higher flow. So if you're filling a system and you need a lot more vapor faster, then this is a little trick that you could use. So by turning the cylinder over and having the gooseneck come down, you would withdraw liquid out of the cylinder, but the rate would be normal, the same rate as you would if you used normal gooseneck. The connection typically is a CGA 705, and definitely a dual regulator would be a good idea when using ammonia. So on to hydrocarbon refrigerants. Talk about them. They've been around since the mid 1800s through to the 1930s. They are very popular now even. They have a very low environmental impact. Again, they're manufactured to be refrigerants. It's not like, you pull the oil out of the ground and now you can use that as a refrigerant. They have to be manufactured to a quality specification. Some of the applications, you start to see domestic refrigerators using isobutane, which is R600A, propane R290, and some of the huge large-scale applications such as liquid natural gas processing, where they're converting natural gas into liquid. Some of those large refrigerant systems, they actually use a lot of ethylene, propylene, those types of hydrocarbon refrigerants to cool the natural gas down to a point where it actually is turned into a liquid, which means it's 600 times lower in volume so that it can be transported across an ocean and have another country or a plant change it back into gas, and it could be distributed as natural gas fuel for consumers in other countries. So very low ozone depleting potential, less than 20 in most cases, the global warming potential, very excellent thermodynamic properties. That's why a refrigerator with a charge of 150 grams can operate efficiently, because the charge is so low. That's all you need for a typical refrigerant. Again, good compatibility with components. You don't have issues with the refrigerant hydrocarbon attacking metals, different metallurgies. And because of the low charges, you can have smaller heat exchangers, and the piping dimensions can be a lot smaller. So the systems can be more economical to fabricate and build. Product safety, very important with hydrocarbons that safety considerations be looked at. Again, it's an A3, which is very flammable. So the system, the room, the application has to be designed specifically for an A3 type refrigerant. And because they are extremely flammable, you must have a lot of due diligence to install and handle and design these type of systems. Some of the detriments that water and uncondensables can cause are definitely they form acids, very similar to CO2 refrigerants. When they're contaminated with water and oxygen. Copper corrosion, if it takes place, can plate out and cause dielectric corrosion on compressors and potential failures. Mercaptants, which are also a type of hydrocarbon, can result in, again, a lot of detrimental effects. Sometimes if mercaptants are in the hydrocarbon system, you'll be able to smell them. They'll have a fuel gas kind of smell, and you'll think that maybe somebody put fuel into that refrigeration system. Hydrogen sulfide, it's a very a dangerous gas and can be formed within a hydrocarbon system if there's some contamination with sulfur in there. It's very undesirable, and again, it's very corrosive. Any weak organic acids that form within a hydrocarbon system and there's oil in there, it'll form a soapy sludge that can deposit in the system. And because in most cases, the piping system are relatively small in dimension, this can cause blocking and basically shut down hydrocarbon systems. And again, sulfur is very corrosive when it reacts with unsaturated hydrocarbons, and this again can cause a lot of detriment to the system. So the ASH AHRI standard 700, it essentially outlines the quality of the hydrocarbon refrigerant, and it's at least 99.5% pure, which is grade 2.5, with minimal levels of critical impurities such as moisture, 10 ppm, and unsuitable hydrocarbons, typically less than 0.5%, as well as sulfur. Another designation for some of these hydrocarbon refrigerants are UL classified, and this comes into play whenever you're manufacturing a piece of equipment. That could be something like a refrigerator or something like that. So whenever you're charging that type of equipment, typically you'd want to use a UL classified R290 or an R600A, which would basically allow you to put that into the equipment and ensure that the equipment warranty is up to date. It's a chart that relatively lists some of the more popular hydrocarbon refrigerants in the marketplace and the typical grades that are available. So a lot of 2.5, so they're all 2.5, they meet that. There's different CGA connections on the various cylinders. And most of the time, like RE170 DME, grade 2.8 is required. And the reason the 2.8 is required, it's similar to ammonia. You can't get a low enough moisture content with just using a grade 2.5 product. Again, bulk grade, in terms of the ethylene, you need to go to a 3.5 in order to get less than 10 ppm water in that. And the grade 1.8 bulk for isobutane, that's really the only grade you can purchase in Canada very easily that I'm aware of. There is some new changes coming to charge limits for flammable refrigerants. There's an international standard, and they're moving from 150 grams to 500 grams. Again, this is a standard and is a voluntary international recommendation. So before these charge limits can come into play, there has to be approval by some Canadian regulations, building codes, the electrical safety code, fire codes. They need to all change. It's predicted that probably in about a year or so, those changes will occur. And this, by having this change made, there'll be even more applications where flammable refrigerants and hydrocarbon refrigerants like propane and isobutane can be used in more applications in the country. So just to kind of review some key things to remember when using natural refrigerants, they definitely have an excellent benefit, and there's a very high performance with these refrigerants and a very good environmental impact. Equipment will differ You cannot replace a refrigerant without making sure that the equipment is designed for use with a natural refrigerant. So none of these natural refrigerants are really a replacement or a drop in. The equipment has to be specifically designed for natural refrigerants. And I can't stress enough safety when handling and dealing with these refrigerants. They are very different than, say, HFC refrigerants in terms of how they're handled and used, different equipment that is used, higher pressures in some cases, flammability, and toxicity as well. So again, safety first, always make sure that you're following the regulation and be aware of the safety requirements when handling these refrigerants. Users of natural refrigerants should always be aware of the quality spec that is required for the application and job. Again, always look at the equipment manufacturing recommendation and basically look at the AHRI standard and the IIAR standard specifically for these natural refrigerants. Refer to the product safety data sheet or the C of A when buying these natural refrigerants. And one of the ways to determine if you are buying the right one is the product name should have R744 in it, or R717, or R290, R600A. That way you know that you're buying a refrigerant grade natural refrigerant. And using the wrong refrigerant basically could, again, void a warranty, affect the operating efficiency, or damage the equipment. One of the interesting things is if you are adding or topping up a system and you're the first gas that you put into the system, each time you add refrigerant and it's a low quality, you're further adding contaminants to the system. So it's just a matter of time until that system corrodes or shuts down, and you get enough non-condensables in there to definitely affect the operating efficiency. So that ends the presentation part. If there's any questions that anybody has, that would be more than happy to answer.
Thank you. And have you got your contact information there so people can reach out after as well?
Yeah.
Great.
I can send the presentation over to anybody as well if they want a copy of that. I think it's also posted on the HRAI website as well.
Mm-hmm. All right. Well, let's hold it open for a couple minutes for questions. If not, give people some time to grab another coffee before they get back to work or the next job. Thank you very much, Bill. I know we had a couple technical difficulties, but everything went great. I really appreciate, HRAI really appreciates you putting this on for us.
Good. Well, hopefully it was of value. And if anybody has any questions down the road, please feel free to reach out to us.
Fantastic. All right. You know what? Looks like no questions. You explained things perfectly. So yeah, Pierre says, thank you. Great job. So this recording will be available on HRAI's website. If you got any other questions, please reach out to Bill there. But yeah, thank you so much again, Bill. And I'm sure we'll see you again.
Great. Take care.
Take care.